Our speaker today is Christopher Schafhauser, and his title you can see there is KK-rigidity of simple nuclear sister algebras. Please, Christopher, go ahead.
Thank you, and thanks for the invitation to speak. I'm happy to be here. So when I talk about this, the KK-rigidity problem of, well, the basic idea behind the rigidity is you want to recover the object from less information than you'd expect. If two sufficiently nice C-star algebras, for instance, are, if you know they're homotopy equivalent, can you conclude they're isomorphic? Or even the problem here, if they're KK equivalent and maybe some extra data, can you conclude they're isomorphic? And of course, you need assumptions, but the answer is sometimes. Probably one of the most famous ones, the Kirchberg-Phillips theorem from probably mid-90s, I think, but sometime in the 90s, that if, there's various versions of it, but if A and B are, let's say, stable Kirchberg algebras, which means simple, nuclear, separable, and purely infinite, C-star algebras, they're isomorphic if and only if they are KK equivalent. There's a KK equivalence, if you like, is the groups, or the group valued functors KK of A blank, KK of B blank are isomorphic. So they have the same K theory in a very strong sense. I mean, they have the same KK theory. Right. So this is, the kind of rigidity statement I want, that if, they agree on K theory in a sufficiently strong sense, they're the same algebra. And the question really is, this is in the purely infinite setting, but is there anything sort of analogous in the finite setting? And the answer is a KK equivalence by itself won't be enough, even for AF algebras. In the finite setting, there's also going to be traceable data and some interaction between traces and K theory, which in some way has to be accounted for. But the hope is KK equivalence in traces, and maybe something else, you can recover the isomorphism type. Right. So call the classification theorem as a partial solution to this. So this is, I'll say many, decades worth of work by the C-star algebra community. Probably definitive results started appearing around 2015. The version I stated will come a little bit later. There was some simplification of hypotheses. But for A and B, let's say unital, separable, simple, nuclear C-star algebras, which this is going to be USSN for the rest of the talk, which are Z stable and satisfy the universal coefficient theorem of Rosenberg and Choquette. Such algebras are isomorphic if and only if they have the same L8 invariant. And here. The L8 invariant consists of the K0 group, the K1 group. I'm going to be careful. Often people include an order structure on K0. Here I just mean the abelian group structure. I'll explain the order in a second. The traces, so these are tracial states, viewed as a compact convex set. And then some extra data, the position of the unit in the K0 group, and a natural pair in between traces and K0. By given a trace and a projection, you can evaluate So the isomorphism of the Elliott invariance, if there's an isomorphism K0 of A to K theory of A to K theory of B, and traces of B to traces of A, so the isomorphism on K0 preserves the sense of unit to the unit, and the isomorphism on K0 and traces are adjoints under this pairing, then the algebras are isomorphic. Right. And I'll add, for historical reasons, the K0 is often included with this order structure, the positive elements being the ones represented by projections instead of formal differences of projections. Under the other conditions, though, you can recover the order structure from the pairing. The positive cone in K0 is exactly the elements that are strictly positive on all trace. For all tau. Okay, together with the zero element. Okay. So nowadays one could drop that from the order, because if in the z-stable setting where which we need for classification anyway, you can actually recover the order. Right. So I'll say a little bit about the other hypotheses here, but the real question is that I'm after is how necessary is a UCT type condition? There's sort of two independent problems here. In the Kirchberg-Phillips setting, you get without a UCT assumption, isomorphism the same as KK equivalence. If UCT held, A isomorphic to A KK equivalent to B is the same as the K theory groups being isomorphic. And actually the Kirchberg-Phillips, the unital version of Kirchberg-Phillips theorem is a special case of this. It's the case when the traces are empty. Everything I'm going to say everything I say will be true in the traceless setting, but I'm going to assume there's at least one trace because the techniques are very different, and everything I actually did was assuming there's a trace. But yeah, anyway, the surprise, Kirchberg-Phillips, to go from KK equivalence to isomorphism, there's no UCT condition. In the classification theorem, even if I replace the Elliott invariant with KK, I don't know how to do this without the UCT. UCT plays more roles than just computing the KK groups. Well, at least more roles than just naively computing KK of AB. You have to compute other KK groups that appear in the proof. But anyway, let me try to say a little bit about the Z stability and UCT assumptions and where they hold first, though. So I'm not going to say a whole lot about what Z stability actually is. There's Z is a Jane-Sue algebra. Z stability means you absorb it under tensor products. I'll just say Z, one should think of as you should think of it as it's projectionless, but you should still think of it as a UHF algebra. I tend to think of it somehow the meat of the two incompatible UHF algebras, like M2 infinity and M3 infinity, and the thing that canonically sits inside both of them in sort of a minimal way. Or to replace 2 and 3 with any other relatively prime supernatural numbers. But more looks, imagine something like this. You take all continuous paths and the, say, 6-adic UHF algebra, which at one endpoint look dyadic, and on the other endpoint look triadic. And that's some non-simple algebra, but there's an endomorphism of this thing which somehow collapses the interval. And if you add an inverse to that endomorphism by inductive limit, what's left is Z. Somehow smashing these two UHF algebras together. And then absorbing this becomes a divisibility-like condition, like Pictoff's condition in von Neumann algebra theory. There's a lot of central matrix units, even though there's not actually projections. But you should the Z you should think of as just being a UHF algebra. That's usually a starting point for doing things with Z. And then the UCT, where's, I'll just say A satisfies UCT if you want essentially some geometric model for the K theory of A. So, one way of saying this is A has the same KK theory as some commutative algebra. And the idea being if, the power of that being once you reduce it to the commutative case, now you can compute this by topological methods, and you actually have a chance of computing what this group is. So there's this, don't want to actually write out the UCT sequence, but KK maps to HOM. There's a kernel X, and probably everyone's seen at some point. But the real point is once you've somehow once you've reduced the computation problem to the commutative case, the topological methods apply, and you can start manipulating this, varying the space X and produce eventually reduce the computation to spheres, and where you can actually compute these things. Anyway, so those are the UCTs, the stability. Let's leave. Then with some examples where this theorem actually applies, this unital or simple nuclear Z-stable UCT algebras. I mean, general rule is what definitely know how to decide when things are unital and separable. There's a lot of machinery for figuring out when things are simple. In dynamical cases, it's freeness and minimality of some sort. Nuclearity is always some sort of amenability. The general rule is if you can write it down, and if it's nuclear and you can actually write it down, the UCT probably holds. So Z stability is actually where the hang-up is for verifying the classification theorem holds in examples. But I'll just give some examples. If I take a cross product, which is coming from a free minimal amenable action of, let's say, a countable discrete group on a compact metric space, this will have everything except possibly Z stability. The UCT comes from a theorem of two out of work on the Baum-Kahn conjecture. The rest of them are much more classical by now. And Z stability holds in some cases. If, for example, there's not a known characterization of when these things are Z stable in terms of actually something we could compute, but there's a lot of sufficient conditions known. For instance, if X was finite dimensional and gamma is elementary amenable. This is a theorem of Kerr and Erskine. So the finite dimensionality of X is necessary. There's counterexamples with gamma being the integers. For free minimal actions of the integers on an infinite dimensional space can have irregular cross product. Whether elementary amenable is necessary, I think conjecturally, no. It's conjecturally this should be for any amenable group, but we don't know. Okay, but that's place where the point is these assumptions actually do hold somewhat generally. What they probably really want to get to is, as I said, whether UCT is necessary or not. And there's no known example of a nuclear C-star algebra where the UCT fails. There are some highly non-nuclear algebras which come from there's a property T obstruction in some cases, but in the nuclear case, we have no idea whether UCT will hold generally or not. And part of what I want to do is ask, if we can't actually just prove the UCT, there is it is it at least true that like structural consequences of the UCT hold without it? I mean, if it's going to be true, there's things we can prove with UCT, we should be able to prove without UCT. And part of I want, it's this theorem. I wanted if I drop the UCT, but replace the right-hand side with, the K0 and K1 replaced with KK theory, is this still true? So here's is UCT necessary? And in the infinite case, the answer is no by the Kirchberg-Phillips theorem. So this is really a problem in the case of finite C-star algebras where there are traces. And let's think this is a conjecture. So same assumptions, but no UCT, unital, separable, simple nuclear, Z-stable. Let's say suppose. So if let's say kappa is invertible and gamma is. So if you have an KK equivalence from A to B and affine homeomorphism from traces on B to traces on A, so they have the same KK theory, the same traces. You'd ask, are they isomorphic? The answer, if you stop here, would be no. You can easily build AF algebra counterexamples. The point is under UCT, for AF algebras, the UCT, or the KK, for AF algebras, the KK theory only remembers the abelian group isomorphism class of K0, whereas the C-star algebra will remember the ordered K0, the order structure on K0 as well. So the traces even in simple cases, the traces in K-theory pairing give extra information, but if I require that kappa and gamma are somehow compatible, I'm not entirely sure what the right notion of that would be in general. So and what compatible means is open, and there's probably the weakest reasonable notion of compatibility, which is enough under UCT, would be that the trace is impaired. You have this compatibility pairing between K0 and traces. So if I take a trace on B and a K0 element in X, or K0 element on A, I can apply gamma to a trace on B, have a trace on A, and apply that trace to X. That's the pairing coming from A. Or I can push X into the K0 group of B and pair it with the trace on B. And ask that those are the same real number. If you assume UCT, this conjecture is true with this compatibility condition, because what you does is we wrote down the Elliott invariance, more or less. If UCT fails, I really don't have a good idea of whether this is enough compatibility or if there's some more subtle. But anyway, it's anything of this sort of spirit is what I'm hoping for. What is true if A and B I suppose. Here. So if there exists an embedding from A to B, so let's say a unital star homomorphism, which is invertible in KK and on trace T of phi. So I have the homomorphism in one direction, which induces the isomorphism in KK and trace. Then A is isomorphic to B. So connection with the conjecture here, I don't know what the right compatibility is going to be in general, but it should be something natural, and then any morphism is natural in this technical sense. Then a morphism at the C star level will induce KK and trace maps, which satisfy this natural pairing by definition of naturality. So it's sort of dodging the question of what the right compatibility condition is, but whatever this is true under whatever correct notion of compatibility means. And the catch is, of course, it's hard to get the homomorphism to start with. But
sorry, you didn't write it, but you said it that phi was supposed to be an embedding. Is hypothesis or just a homomorphism?
Well, the algebras are simple, so if it's any homomorphism, it's injective.
Sorry.
Oh, no, you're fine. Yeah, I beat sloppy, but yeah, unital star homomorphism, which is necessarily an embedding. But I'll say one case, then you can pick off this if say if I restrict to the unique trace setting, which these classifiable algebras, I mean, the finite one, the ones they tend to have at most one trace. If there's a trace at all, it's usually the unique trace somehow. We can build things with arbitrary trace simplex, but they're sort of often by artificial constructions, or very carefully rigged dynamics. But anyway, in the unique trace setting, if A is homotopy equivalent to B, then it's isomorphic to B. And the point is the homotopy equivalence comes with the homomorphism A to B with a homotopy inverse. In particular, the homomorphism from A to B is invertible on KK, because KK inverse is the homotopy inverse. It has to induce an isomorphism on traces if these traces are 1-point sets. So the homotopy equivalence is going to give an isomorphism, or prove the existence of it at least. You could weaken this unique trace to asking that projections separate traces so the K0 recovers the tracial data, or even just drop all the trace conditions, but require there's a homotopy equivalence which happens to preserve trace or be an isomorphism on traces. Okay. But what I want to do for us at the time is give some general idea of what goes into this, and not into much details, but just sort of try to get a big picture of how one obtains this isomorphism from this one-sided embedding. The first reduction, it's enough to show there exists embedding in the other direction, so that of course, we're aiming for is embedding in the R direction, which is a two-sided inverse. That actually doesn't have to exist because there's phi doesn't have to be surjective. But it's enough to get a left inverse up to approximate unitary equivalence, meaning there's a sequence of unitaries in A so that it's in norm these. So these conjugates of psi act as left inverses of phi in the limit, pointwise and norm. There's a subtlety here, but which I'm going to mostly ignore. But if I have the psi, it induces maps from in KK and trace as well. Traces is invariant under approximate unitary equivalence. And it's invariant under unitary equivalence clearly, and it's everything's continuous enough you can push through a limit. So phi and psi are inverses of each other, or well, psi is a left inverse of phi on trace, and phi was two-sided invertible on trace. So psi is necessarily invertible on trace. And more or less, you can say the same thing in KK. In KK, you'd want to say in KK, psi phi is the identity, but phi was invertible, so psi must be. There's a glitch coming from KK not being invariant under approximate unitary equivalence, but there's enough to here to conclude at least that psi is still has a two-sided inverse in KK. But basically, the fact that phi is invertible and KK and trace, and that phi has a one-sided inverse forces that one-sided inverse to also be invertible, modulo some technical KK issues. The point is the one way or another, psi you built is necessarily invertible on KK and trace. And once now everything was all the assumptions were symmetric in A and B. So if I can get a one-sided left inverse for phi, I can also get a left inverse for this psi. But then if I look at phi prime psi phi, that's on the one hand equivalent to phi. If I use phi prime psi as the identity, and on the other hand equivalent to phi primes, and psi phi is the identity. So what you have is phi and psi are left inverses of each other up to approximate unitary equivalence. And then this is Elliott's intertwining argument. If phi and psi are inverses up to approximate unitary equivalence, then the algebra, if there's inverses up to approximate unitary equivalence, then the algebras are isomorphic. And the idea is you just inductively conjugate phi and psi by unitaries to build sequences phi n and psi n, which in the limit act like inverses of each other. And so at the phi n's and psi n's are pointwise Cauchy. So take a pointwise, the pointwise limits are necessarily inverses of each other. But you can desymmetrize this thing instead of looking for a two-sided inverse, look for a left inverse up to equivalence.
One little question. In the Kirchberg-Phillips setting, if I remember correctly, KK identifies with homotopy classes and also with classes of morphisms up to approximate unitary equivalence. Does that hold in this context, in this more general context too?
It's a it's a bit subtle. There's two things happening, even in the Kirchberg-Phillips study. There's the difference between approximate unitary equivalence with sequences and the asymptotic unitary equivalence with continuous passive unitaries. KK is the equivalence under continuous passive unitaries. If you go sequences, you have to pass to some quotient of KK. But even with that modification, it doesn't quite hold here, even under the UCT. There's determinant-like information that the KK and trace themselves can't see. Well, if I can write there's a this variation of algebraic K1, which is the infinite unitary group modulo the closure of the commutators. The closure being in the inductive limit topology. If I have under UCT at least, I have two maps from A to B, which agree on KK, trace, and this Hausdorffized algebraic K1, then they're approximately neutral equivalent. But there is extra obstructions here. In the purely infinite case, this group is technically still there, but it collapses to operator K1.
Thanks.
Yep. This is part of the reason why it's hard to just remove UCT from the classification theorem by adding KK to the invariant, because there's this type of group has to appear somewhere, and how it's captured in KK is less clear. At least how it's captured just from the KK class of the algebra is far less clear. But I'll actually say more about that in a second, but so there's another reduction one can make, which I'm going to write here a slight oversimplification, but that's okay. Instead of trying to construct psi as this genuine homomorphism psi as an approximate left inverse of phi, it's enough to construct an approximate morphism psi, which is an approximate left inverse. So same kind of condition, except now psi is maybe a UCP map, which epsilon preserves products on finitely many elements or something. Or there's a sequence of psi's which in the limit act like a homomorphism, and the limit act as left inverse to psi. Or another way of encoding that, it's enough to build psi from B into the sequence algebra of A, bounded sequences, modulo null sequences. Or if you prefer, you can stick an ultra power there instead.
Sorry, would this be like an asymptotic homomorphism? I mean,
yeah, exactly.
An easy or elegant.
Yeah, an asymptotic morphism would get up too, but it's actually, there's technical reasons I want to work sequentially instead of along a continuous path, but it's there's basically that kind of idea. So it's enough to get some kind of asymptotic left inverse instead of a genuine one, and up to some A. Using notation now, the identity ambiguity and map into the sequence algebra, but right. And well, that alone's not enough, but well, you also want some condition about psi being unitarily equivalent to subsequences of psi, but I'll leave it here for now. And what passing to this asymptotic algebra or sequence algebra is going to by me is that, these algebras were all simple. So these KK theoretic, extension theoretic methods don't tend to buy you a whole lot because the most powerful tool you have is a six-term exact sequence, and there's no ideals. There's nothing to apply that to. The sequence algebra does, in the finite case, does have a natural ideal in it. It turns out to be very well behaved. So-called JA. There's all the trace zero elements on all traces. And I wrote all traces on the sequence algebra here, but in the there's an obvious collection of traces where you fix a sequence of traces on A. You apply the nth trace to the nth term of the sequence and then take a limit point under a Z stability condition, which I'm still assuming, though such traces are dense in all the traces. So this all traces on the sequence algebra is something we actually can compute. But that turns out to be an ideal, and the quotient has von Neumann algebra-like properties. If A was if A had unique trace and I did an ultra product version of the ultra limit version of this quotient would be R omega, where R being the hyperfinite 2-1 factor. In the general case, you get some kind of fiber bundle, like continuous field of over the traces with R omega as the fibers, roughly. But basically, there's enough, the quotient somehow is close enough to being R omega that von Neumann algebraic techniques do work. And the ideal turns out to have other special properties that give a very rigid extension theory and analogs of like Voigt-Kolasky's theorem and the BDF theory. And but so our key tool then is from me with Karian, Gabe, Dequitius, and White from it's about 2 years, paper appeared about 2 years ago now, maybe a year and a half ago. Yeah, probably a year and a half ago. So same assumptions, A, B, unital, separable, simple, nuclear, Z stable. Let's say finite, so there's traces. And the problem is I want to classify all maps from, let's say, B to A infinity. So I'm still in a situation I have this embedding of A, and I had this embedding of A into B that I'm trying to build a approximate left inverse for. And what I'm going to do is split this problem into pieces and look at maps from A into the quotient and maps, and then lifts of along this ideal. And the theorem comes in a few parts. There's a complete description of maps, say unital homomorphisms from A into the quotient are completely determined by traces. These are the continuous up to unitary equivalents, or the continuous affine maps on traces. In fact, the quotients of A infinity and A infinity have the same traces, with the isomorphism being the obvious one. You look at the induced map on traces, but yeah, I can build maps theta into the quotient with prescribed tracial behavior, and those maps are unique up to unitary equivalence. The next problem is, okay, if I have a map into the quotient, can I have the problem from, say, BDF theory, can I actually lift it along this extension? I mean, if this was the compacts inside B of H, you have a map to the Kalkin algebra, lifting has this X obstruction. there's in general here an obstruction on X to B into this ideal JA if you're don't worry too much about separability issues. But it turns out there's enough rigidity, extension theoretic rigidity here that this X element vanishing, this is enough to conclude the lift actually existed. You can turn the homotopy class, homotopy equivalent to a lift to a split extension is actually enough to force you to be split for this particular extension. And you can repackage it as a KK problem and show there's a lift psi from B to A if and only if there was a lift at the level of KK theory. And another condition. When I'm writing homomorphisms, I've probably said this out loud a few times, but I'm implicitly assuming all my homomorphisms are unital. I preserve the unit. At the KK level, I need some version of preserving the unit to have a chance of doing this, and that's that kappa preserves the units on K0. So a unit preserving KK lift of theta is enough to guarantee there's a unital star homomorphism lifting theta. And you can even choose psi to induce kappa. And the final one, once you have one psi, you can ask, how unique was it? If I took a second lift phi, then they'll have a formal difference phi psi from A into this ideal. And what you end up with actually is the homomorphisms, the homomorphisms from A into A and B into A infinity. The phi from B to A infinity with the same trace as psi up to unitary equivalence is exactly the KK maps from B into the quotient. This map here with prescribed traces, which 1 and 2 let me build, I can parameterize all of them exactly by maps into the ideal. So this is isomorphic to the set of, and then there's another unit issue. Since all my maps are required to be unital, I want the maps into the ideal to vanish on the unit. Right, so this is a bit of some formal difference with psi. So it's a bit technical altogether, but the takeaway of it is I have a complete descriptions of maps B into A infinity in terms of, well, traces and some kind of secondary KK invariant. And then that gives me, strategy for building this left inverse of P, where the setup I was in, remember, was I had a P invertible in KK in trace, and I'm trying to build a psi from B back to A or A infinity, which inverts it. And what I'm going to what I can do is, let's see, I have the inclusion as constant sequences from A into sequence algebra, and induce map to the quotient there. Let's make that be a little bit shorter. So I'm looking for a map B to A infinity so at that upper left triangle commutes up to unitary equivalence. So there's this approximate left inverse for phi. And what I can do is, using the previous theorem, phi is on traces, phi is invertible. So if I take phi inverse followed by the qi, I have a trace map from B to A infinity, trace map from B into the quotient by the first condition. I can maps into the quotient are determined by tracial data. So I can build this map into the quotient. And then since they have the same traces, by the theorem applied to maps from A with A in place of B, both ways around the triangle agree on traces, so they're unitarily equivalent. The second part was a lift of theta exists if and only if there's a KK lift. So I have this theta here. It has a KK lift, which is phi inverse followed by iota, since I assumed phi to be invertible. So there's some lift here by 2, so that this, well, this even commutes on the nose. And except the issue that the psi you build doesn't make the upper left commute, probably, but I have 2 lifts of phi theta now. They have a formal difference from A to J, and I can systematically use part 3 to adjust psi so I don't screw up the lower triangle and what makes the top triangle commute. And then here's the psi that is the approximate left inverse you need. So you have a psi from B to A infinity with psi phi. Which is what, say iota A, which is what I said you need. I'll just end with the 30 seconds I have left. This theorem, but on how you lift is really, it's really systematic use of this is underlying the whole thing. The theorem from the 5S was part of our new proof of the classification theorem under UCT. We classify maps from A to B in terms of various data, but the underlying thing was classify approximate maps from A to B up to unitary equivalence by traces in this KK of A J group, or KKBJ here. So this algebraic K1 group I mentioned briefly that shows up as an obstruction to approximate equivalence of morphisms, that data is encoded here. It's this the K1 group of this the trace 0 part of the sequence algebra is somehow where all the algebraic K1 ends up appearing. And this is somehow the reason why it's becomes hard to remove the UCT is you assume something about A and B having the same KK class, but how the KK class of B relates to the trace 0 elements in A, or approximate trace 0 elements in A becomes far less clear. That it's really understanding these kind of KK groups is where this extra UCT condition shows up that just didn't appear in the purely infinite setting, like the Kersberg-Phillips theorem. Right. So I'm out of time though, so I should stop here. But thank you.
Thank you very much for your nice talk. Are there questions from the audience?
Oh yeah.
See, is there anything in the chat? So I have a little question. So one, can you pull this down so that we see the 3 or 4 things that were included in this lemma here?
This one?
Yeah. Oh, yeah. Okay.
Right, zoom out and get the whole.
And the 2, yeah. 2.
Yeah.
So Yeah, so the 2 says that you can that the existence of a KK class that does something implies the existence of a morphism that does something, but an algebra morphism that does something.
Right.
So is it true that these KK groups, this with when on the right you put A infinity, every class there the class of an actual homomorphism?
Every class here, no, that shouldn't be. Not every class here will be a class of morphism. I mean, there's the unit issue for one, but then I think even without that, it's true that every I didn't write it, but you can take the lift you build to induce the given kappa. So what it's going to under UCT, what it is the maps which maps here which where there's a compatible trace map will come from homomorphisms.
There is a question in the chat from Yan Chao. Are there natural examples of homotopy equivalencies between USSA Z-stable sister algebras which are non-isomorphic on the trace simplices?
I don't know any really natural example off the top of my head, but one could build them. You take, by building the Elliott invariants. Imagine taking the K, the K theory of the Jane-Sue algebra, but with 2 extremal traces. Compared to, so you have something like K0 of A is the integer is generated by the unit. K1 of A is 0. Trace is so two extremal traces. So traces are an interval. A will be homotopic to the Jane-Sue algebra. The only difference being that it had unique trace. But or you could do all sorts of the key is you need one of the algebras to have the property that projections don't separate traces. And there's probably dynamical ones one could construct, but certainly many exist from inductive limit constructions.
So how hard is it to show they are homotopy equivalent in this case?
I think what you wouldn't. What we would need is so this classification theorem tells you what all the embeddings look like up to approximate unitary equivalence, not just what the isomorphism classes are. There's variations of it which will tell you what the embeddings look like up to asymptotic unitary equivalence. In particular, you'll get a way of checking if the embeddings are homotopic. And once so if you take that theorem telling you the embeddings up to asymptotic unitary equivalence, then it's a matter of just playing with the algebra. The maps exist, the homotopy equivalence exists at level invariant, and then you can just put it together. There may be, I wouldn't be surprised if there's examples one can build where one could just write down the homotopy without abstract machinery too. But
so it's sort of like a Elliott intertwining argument, but at the level of homotopy. Is that something that will be required?
Yeah, but you need more rigid than homotopy. I mean, doing the intertwining at the level of homotopy probably doesn't work, but at the level of asymptotic unitary equivalence. So it just, with the homotopy by a path of unitaries, then all the intertwining machinery works.
Okay, thanks.
Yep.
Okay, are there any more questions? Otherwise, I'll stop the recording here.